these are your Chapter 1B notes. The majority of these notes will be dealing with absolute value equations, and then along with just a process of isolating a variable, getting a variable by itself, not necessarily solving for a variable, but just writing a formula in terms of a different variable. So absolute value, the definition of absolute value is that it's the distance c numbers away from 0 on the number line. And so you're talking about distance. Anytime you talk about distance, whether you're going forward or backward, left or right, it's always positive. So it's always a positive measurement. So absolute values cannot be negative. So if you look at this number line, we're always talking about the distance away from 0. It's always in terms of 0. So those two vertical lines around a number or around an expression is asking how far that expression is away from 0. So if you look at number 1, it's asking for the absolute value of a, and the absolute value of a is the distance a is away from 0. So if we count backwards from a back to 0, you can see that it's 6 units away. The negative in front of the 6 is just really telling us direction, that we were 6 units away to the left. But when you write down the absolute value, it's just a positive value. For the absolute value of b, it's how far away b is from 0. And so if you look at b and count back to 0, it was 1 unit away from 0. It was a positive 1, but it's still positive 1. It doesn't change to the opposite sign. It's always in terms of a positive value. And c is at positive 6, and so it is 6 units away from 0 in the positive direction. So if you look, A and C both have the same absolute value because they are the same distance away from 0. One went to the left and one went to the right. Number 4, I guess, is just a repeat, is 6. The absolute value of negative 3 is asking how far is negative 3 away from 0, which is 3. Number 6, we've got to do a little bit more math before we can answer the question. It didn't really say an actual number on the number line. It gives you an expression. So we first simplify the expression. 4 take away 9 is negative 5. And now we can say that the absolute value of negative 5 is 5 units, because negative 5 is 5 units away from 0 on the number line. 7, 8, and 9 kind of complicate things. What I've talked about so far are things that you should know from previous years or from middle school when you first got introduced to this concept of absolute value. But when we get into 7, 8, and 9, we're talking about the unknown value is inside the absolute value. In the first 6 problems, the unknown value was on the outside. It was asking for the absolute value. So it's a little bit different when the unknown is inside the absolute value. So in number 7, it's asking what number or numbers have an absolute value of 5. They're giving us the absolute value. We got to figure out what applies to that. So if I look at the number line, I can see that 5 is 5 units away from 0, but so is negative 5. And so there's actually 2 numbers that have an absolute value of 5. So x could equal 5, or x could be negative 5. So because there's 2 choices, we have to come up with all of the choices. And so how you can write that is in a solution set, just like we talked about when we were solving equations. Since there's 2 answers, that's the proper way to list them. 7 was pretty easy, really no work involved, but it kind of leads us into 8 and 9 and more complicated problems. For number 8, I think you guys can all say that one of the solutions, just by guessing and checking and looking at it, is 4. Because if you put a 4 for the x and you add 1 to it, you get 5. The other side, the negative value, is a little bit more difficult to figure out. A lot of people want to say negative 4. But if you add 1 to negative 4, you actually get negative 3, not negative 5. So guess and check when you get more complicated values inside the absolute value is not the best method. What you can do is use the definition of absolute value. And you say the absolute value of this expression, the absolute value of x plus 1 is equal to 5. That means that x plus 1 could be 5 units to the right, or x plus 1 could be 5 units to the left at negative 5. So that expression inside the absolute value could equal 5, or that expression inside the absolute value could equal negative 5. So what that does, by writing two equations, you can see that I'm interpreting the absolute value, I no longer have those two vertical bars. So when you rewrite an absolute value equation as two separate equations, now it's simply just using inverse operations. We can get 4, which we knew just by guessing and checking, common sense, but we also can get negative 6. What's nice about using algebra and using equations, the whole concept is that it takes less time and less error. So it's more consistent, and it's going to be correct. And again, that equation, that expression is not too complicated. Even number 9 is not too complicated. But when the expression gets more involved, it's a nice, easy system that'll work every single time. So you don't have to worry about guessing and checking. For number 7, I agree, guess and check is the best method. There really isn't a whole lot of work to show. But when they get more complicated, if you can think back through these terms, what an absolute value is. It's the distance a number is away from 0. There's two ways to go on a number line, to the left and to the right of 0. So each of these numbers has two absolute values, except for one number. The only number that doesn't is 0, because in terms of 0, it's 0 away from itself. So for number 9, we're going to use that same process of writing two separate equations. We're going to use algebra. So it's asking, the question's asking, what would you subtract 2 from to equal 4? What absolute value, when you subtract 2, will equal 4? What values of x will this be true for? So that thing, in order for it to have an absolute value of 4, must be equal to 4. That would be if it was 4 units to the right, or that thing would have to be 4 units to the left. So the quantity inside the absolute value equals 4, or it equals negative 4. It went 4 to the right, or it went 4 to the left. And when you do that, you solve the simple equation that's formed, x equals 6, or when you add 2 to negative 4, x equals negative 2. So you have two solutions. We put them in a set notation. Okay? We should always check our solutions. You can check by plugging them back into the original problem. So if I were to plug 6 into the original problem, 6 minus 2 is 4. The absolute value of 4 is 4. And if you plug in negative 2 minus 2 gives you negative 4, which is the absolute value is 4. So I just kind of reiterate that in these directions so you have something to refer to. And again, if you can see, number 2 gets a little bit more complicated, and 3 on the next slide is even more complicated yet. So here's your process. The nice thing about algebra, it's the same thing over and over and over again. So the very first thing you're going to do in order for this to work is you want to have the absolute value equal to something. So if there's something else with the absolute value, you're going to use inverse operations to get rid of it. If you can see in example number 2, the 3 sitting out in front of the absolute value is being multiplied. You cannot distribute. The distributive property does not work with absolute value signs. So we'd have to get rid of that 3. It's being multiplied. You use inverse operations to divide. Once you have the absolute value isolated, you're going to rewrite as two separate equations. One set to the positive value and one set to the negative value, because you're talking about if it was to the right or to the left of 0. You're going to solve each of those equations, and then you're going to check your solutions because they could be extraneous. And the term extraneous solutions, you did nothing wrong mathematically, but for whatever reason, it does not work when you check it. This happens when we force sign changes. So because an absolute value is always positive, it does sometimes tend to give us extraneous solutions. So we always check. Notice we didn't have to write down a formal check. We can plug it in our calculator. You can do mental math, but you need to check, because if you don't, you could get it wrong on your homework or a test or quiz. After you check your solutions, you put the solutions in a solution set or graph it on a number line. So you could have two solutions because it's to the left and to the right. You could have one solution because maybe one of your solutions were extraneous, or maybe you're dealing with an absolute value of 0. And you may have 0 solutions, no solutions, because both of them were extraneous. So you could have 1, none, or 2 solutions for your answers. All right, so number 1, let's try it. It's already isolated. So they're asking for y, the absolute value of y plus 3 is equal to 8. So basically they're saying this thing here could equal 8, or that thing there could equal negative 8. That's what we want. So those are our two equations. So y plus 3 is equal to 8, or y plus 3 is equal to negative 8, because those are the only two values that have an absolute value equal to 8. If it's y plus 3 equals 8, when we subtract 3 from both sides, y is equal to 5. And then if we subtract 3 from negative 8, y is equal to negative 11. We plug them in. 5 plus 3 is 8. Absolute value of 8 is 8. And negative 11 plus 3 is negative 8. So it works. And so our solutions are 5 and negative 11. To show that on a number line, we could just simply put a dot at negative 11 and a dot at 5. I just want to show you graphically a picture of what that solution looks like. I don't worry about all the numbers in between as long as the negative is to the left of the positive. Number 2, before we begin solving, we need to isolate the absolute value. So like I was saying before, it's 3 times the absolute value. We're going to divide by 3, both sides. This 3 cancels. We're left with the absolute value of p minus 5 is equal to 2/3 p. I know it's not pretty, so a little bit more complicated. This one would be difficult to guess and check. You got a variable on both sides. So we go back to the basics and say, well, every number except for 0 has 2 absolute values. So p minus 5 would equal 2/3 p. That would be the absolute value to the right. Or p minus 5 is equal to negative 2/3 p. That would be the number to the left of 0. Now when we solve it, we got that ugly 2/3. Not a big fan of solving with a fraction. So I'm going to use that trick from yesterday where I make everything 3 times as big. So if you remember, we divided by 3 in the very beginning to get the absolute value by itself. I'm going to just multiply everything by 3 just to make things 3 times larger. Now that I don't have an absolute value symbol, the distributive property will work. 3p minus 15 is equal to 2p. And so now I can solve using inverse operations. I'm going to bring my negative 2p to the left, and I'm going to add 15 to the right. It just seemed easier. That means p is in terms of a positive number, and p is equal to 15. When I plug in 15 into the original, we always go back to the original. So when I plug 15 in here, 15 minus 5 is 10. The absolute value of 10 is 10. 10 times 3 is 30. So when p is 15, I get 30 here. And when I plug 15 in over here, 2 times 15 is also 30. So they balance. That means it's correct. I do the same thing for the other side. So I'm going to multiply both sides by 3 just to get rid of that ugly fraction, make it 3 times as large. So I get 3p minus 15 is equal to negative 2p. And so this time I'm going to add 2p to both sides. You could actually bring the 3p over, it doesn't matter. And I'm going to add 15 at the same time. So that way I have my variable 5p on the left, and I have 15 on the right. Divide by 5. Divide by 5. P is equal to 3. When I plug 3 into the original equation, you always go back to the original. 3 minus 5 is negative 2. The absolute value of negative 2 is 2. 2 times 3 is 6. So I got 6 on the left-hand side, and when I plug 3 in times 2, it's also 6, so they both work. So I include both 3 and 15 as my solutions. Got one more for you, a little bit more complicated. So we have an absolute value quantity is equal to some other crazy quantity. I want to mention that this is actually one whole number. It's equal to that, whatever negative 2 times the variable is plus 3. So that's one whole number. So when we rewrite this, we can talk about that number, negative 2m plus 3, but we also want to talk about the number to the left, and the number to the left would be the opposite of that number. A lot of times people will just change that opposite sign out in front of the 2m, but really you have to change the opposite of everything. It's the opposite of the entire number. So by putting parentheses around it, I can treat this as a negative 1, and I distribute that negative through the entire quantity. Anytime you have a negative quantity, you have to apply the negative to every number inside that quantity. So just to clean up this side, 15 plus m is equal to positive 2m. Everybody gets the positive 2m right, but that positive 3 turns into a negative 3. Big difference there. So I'm going to go ahead and solve. I'm going to go to the other side now. I am going to add 2m to the m, and at the same time I'm going to subtract 15. You could do this in 2 steps. You don't have to do it this way, but it kind of cleans up both sides at the same time. The 15s are gone. I'm left with 3m equal to negative 12. Divide by 3. M is equal to negative 4. We'll check that answer in just a second. Let's go ahead and solve the other side of this equation. So I'm going to actually bring the m over to the positive 2m. So I'm going to subtract m from both sides. That puts my variable on the right-hand side. And so since my variable is on the right-hand side, I want to move this positive 3, or move the 3 over to the left-hand side. So I'm left with 18 is equal to m. More than one way to do those steps there using the inverse operations. So I'm going to check my solutions. Again, there's variables on both sides, so checking it is a little bit difficult. You have to plug it into both sides and see if they match. So when I plug negative 4 in here and in here, when I plug negative 4 in for 15, 15 plus negative 4 is the absolute value of 11. I'm wondering, is that equal to negative 2 times negative 4 plus 3? Negative 2 times negative 4 is 8. 8 plus 3 is 11, and the absolute value of 11, so it checks out. So negative 4 works. When I check 18, 18 plus 15, I'm wondering if the absolute value of 18 plus 15 is equal to the same thing as negative 2 times 18 plus 3. Well, this is negative 36 plus 3 is negative 33. And I already know, without even adding these two together, which I can, but an absolute value of 33 is positive 33. I have a positive 33 equal to a negative 33. That does not work. So this is the type of extraneous solution that you might see, where the signs don't match up. So you simply just eliminate that solution from your solution set. And so the only solution we have this time is negative 4. Okay? So that's absolute values. And then the last thing I just wanted to add here is sometimes you're asked to represent a function or a form of the equation in terms of a different variable. So if you look at these 3 examples, right now, part A is not in terms of any variable. So if it asks you to solve for a desired variable, it means get alone, get variable alone, or isolate the variable. So in this particular case, they're asking us to solve for y. We want to get y equal to something. So we want this equation written in terms of y. It's a little complicated, but it helps you understand inverse operations and order of operations. So if I want to get this y by itself, the very first thing I would do is add 2n to both sides. The problem with this, a lot of people don't like the fact that you can't add 9 and 2n together. So we just rewrite them as 4y is equal to 9 plus 2n. You could also put the 2n out in front. Now to get y by itself, I just use inverse operations. I'm going to divide by 4 and divide by 4, and there's your expression. Y is equal to 9 plus 2n over 4. If you want to divide the 9 and the 2n both by 4, that would work too. So you could have the expression 9/4, leave it like that, plus 1/2 n, because 2/4 reduces to 1/2. So I like improper fractions in simplest form, or, we always simplify. So either one of these two answers would be correct. Part B, you have, they want you to solve for little b. So we want to get this variable by itself. I see the a there is added to it, but we're going to take care of the a last here. I need to get rid of that stuff out in front. And so the stuff out in front is multiplication. I'm multiplying by 1/2 times h times this quantity. So if I'm multiplying by 1/2 h, if I divide by 1/2 h, that'll go away. Whatever I do to one side, I also have to do the other. And so when you divide by 1/2 h, dividing by 1/2 is the same thing as multiplying by its reciprocal. So actually what that cleans up to be is 2 times capital A all over h. The h is still in the denominator. If you didn't like what I just did there, you could times both sides by 2 to get rid of the 1/2, then divide by h to get rid of the h. I kind of took care of all of it at the same time. This is equal to a plus b. And so now we can subtract a from both sides, little a. Little a has nothing in common with those other a's and h's. And so b is equal to this crazy quantity, 2 capital A over h minus a little a. So it gets a little bit difficult. I'm going to have you guys solve for little a for part C on your own. That's going to be part of your problem. And you're going to do the summary problem as well. So answer this question. What number is the only number that doesn't have 2 absolute values? And then I want you to solve this absolute value and example, that last example, part C. If you would do both of those. Good luck.